In this lecture, we're going to learn about orthogonal projection. If u and v are vectors in the Euclidean plane, so u and v are vectors, and v is non-zero, we can project the vector u onto v. Okay, what does that mean? Let's draw a graph here. Okay, let's say this is our vector here, v. Okay, just some non-zero vector. And let's say we have a vector u like that. Okay, now when we take u and consider what happens if you draw an imaginary line down to v. Okay, from the point u, draw a perpendicular line straight down to v. Okay. Now, when you do that, you get this new vector. Okay, this little vector right here. And it's pointing in the same direction as v. This is called the projection of u onto v. Okay, think of u being smashed down to v. Okay, u is being smashed down to this vector v, and that resulting vector is called the orthogonal projection of u onto v. Okay, the orthogonal projection of u onto v. And it's denoted like this. Okay, projection of u onto v. There's a formula for this, and it goes like this. The projection of u onto v is equal to u dot v divided by v dot v. Okay, that scalar times v. Okay, so it's a scalar multiple of the vector v, which makes sense since this projection is pointing in the same direction as v, so it's going to be some scaled version of v. Okay. We can extend the notion of orthogonal projection to any inner product space by defining the projection like this. Projection of u onto v. Instead of using dot product, we just use inner product. U, inner product with V, divided by v inner product with itself times the vector v. Okay, so it's a scalar multiple of v. Let's do an example. Consider P2 with the inner product given by this. Where P is this polynomial. And Q is the polynomial with the coefficients corresponding to B. Let P be this particular polynomial, and let Q be this particular polynomial. And let R be this. Find the projection of P onto Q, and find the projection of P onto R. Okay, so let's look at the first one, projection of P onto Q. That's the inner product between P and Q divided by the inner product between Q and itself times Q. Okay. Now let's rewrite P with all the coefficients. So here it has no constant term, so that's going to be 0 plus it has 1x plus, and it has 3x squared. Q, well, it has no constant terms. It has no x terms, but it does have one x squared term. Okay, so let's do P inner product with Q. Okay, look at the corresponding coefficients, multiply them, and add them up. Okay, so we just get 3. Q inner product with Q, same thing, 0 times 0 plus 0 times 0 plus 1 times 1, which is 1. Okay, let's plug that all into here. So we get the inner product between P and Q, that's 3. Inner product of Q with itself is 1. And then we have Q itself, so that's just the polynomial x squared. So we get 3x squared. Okay, so the projection of P, this polynomial, onto Q, that's this here, x squared. When we take P and then project it onto Q, we get 3x squared. Okay. Okay. So now let's find the projection of P onto R. Okay, using the formula for projection, we get P, inner product with R, divided by the inner product of R with itself, times R. Okay. Let's rewrite P. And R. Okay, R was just negative 5x, so that's going to be 0 minus 5x plus 0x squared. The inner product of P with R, let's look at the coefficients. Multiply them out, so 0 times 0 plus 1 times negative 5 plus 3 times 0. So that's negative 5. Inner product of R with itself, 0 plus negative 5 squared plus 0, that's 0. So we just get 25. Let's plug those values in here. We found the inner product of P with R to be negative 5. Inner product of R with itself to be 25. And then we have R itself, which is just this polynomial, negative 5x. Okay, simplify a little bit. And we get x. Okay. So look here, the projection of P, which is this polynomial, onto R, that's this polynomial, negative 5x. When we take P of x and project it onto R, we get just x. Okay, in other words, when we take this polynomial, P of x, and then we smash it down to R of x, we just get x.